Alright, so we're going to review factoring briefly. So we basically have two scenarios, and one is the first when you don't have an a value here that's different from just one, because we know we have an invisible one here, but this is kind of the standard, most basic way of factoring a quadratic. So we'll do this one first, and then we'll get into when we have an a value in the front that's more than 1. So don't forget that when we are working with quadratics, we're multiplying to this number, and then we're going to add. So I'll write multiply, and then we are adding to the middle number. So what I'm going to do first here, since I know I'm multiplying to 24, is I'm going to look at the factors of 24. So we obviously have 24 and 1, 12 and 2, 6 and 4, and then we have 8 and 3. I think that's all. So we want to look at these combinations and see which pair of these together, whether positive or negative, could make a -5. So if we had positive 24 and positive 1, that would make 25. If we had one of them negative, we'd have some version of 23, etc. So you're going through in your mind and seeing if we use plus and minus signs, which one will get us to -5. So 8 and 3 will get us to -5 if we have a -8 and a positive 3. Because those combined together will get us a -5, and they'll multiply to give us a -24. So since those are my two numbers that I've unlocked here, I'm going to put this into parentheses and drop my two numbers in there. I have a -8 and a positive 3, so -8 plus 3. And that would be your final answer if you just had to simplify the quadratic equation. But let's say that you had been given this in the first place equal to 0. Then, after you factor it, so this is step 1, you're going to then take your parentheses, and they're equal to 0 since our original problem was equal to 0. Since they're being multiplied, we can take each of these parts and equal them to 0. And now we can add 8 over here, and one solution is x equals 8. And over here we can subtract 3, and we get that x equals -3. So when it's equal to 0, you have to take it all the way down to this step and get solutions. If it's not equal to 0, if this is not there, all you're doing is rearranging it to write it in the parentheses. Now, if you wanted to check yourself and make sure it worked, you can multiply all of this back out again with FOIL, and we'll get x squared plus 3x minus 8x minus 24. And then when I combine that, I'm back to my original problem, so we know we factored it correctly. All right, if we have a quadratic that has an a that's greater than 1, so here our a is 3, it's a little bit different. So we're still adding to this, but now we're going to multiply to whatever this times this is. So it's not just the end anymore. We have to take into account that we have a 3 here. So -12 times 3 is -36. So we're looking for pairs that will multiply to -36. So we could have 6 and 6, 12 and 3, 4 and 9, 36 and 1, 2 and 18. I think that's it. So this process is a little bit different, but it ends up kind of going back to the same thing. I'm going to go ahead and drop down my 3x squared and my -12 and keep those in the mix. And then what I'm going to do now is rewrite 16x with the two solutions that I found that work from over here. So which combination of these will give me a positive 16? It'll be plus 18 and minus 2. Now, since I went ahead and said that this is my pair, You want to make sure too, so look at the signs that you've assigned them. It should work to add here. So plus 18 minus 2 gives me a positive 16, so my sign is good there. And then make sure that these two numbers multiply and give you the same sign as your product. So plus 18 times negative 2 gives us negative 36, and that was our product here because we had negative 12 times positive 3. So our sign matches here and our sign matches here, so we've picked the right two numbers. Now, since we really took this from 16x, these need x's, and we've basically done the opposite of simplifying. So we took 16 and we spread it out into two different numbers. And so what we're going to do now is look at our first two as a pair and our second two as a pair. So looking at our first pair, let's see what these two have in common. So they both can divide a 3 and they both can divide an x. And if I was to divide that out of both of them, left over I have an x and I have a 6. Now here I can divide out a negative 2, so negative 2, and left over I have an x and a positive 6. This is positive because if I was to multiply my negative 2 back to my positive 6, I would get negative 12. Now this is a good checkpoint for you because these two parentheses now should be the same. If they're not the same, go back and see if you messed something up with a sign. Maybe you picked the wrong numbers from over here, but there was probably some problem happening there. I'm going to zoom in on this side. All right. So once we're here, we can treat x plus 6 as something that's been distributed to both of these pieces. So we can go ahead and factor it out to the front. So I'm going to take this out of both of those terms. They move to the front. And left over, I have a 3x minus 2. And it's completely factored. Now, just like we said before, if our original problem had been equal to 0, and we were solving for solutions, we need to set this equal to 0. And when we do that, we can take each part and solve for x. So here I get x is negative 6, and over here I'm going to get that x is 2/3. So those would be my two answers for this equation. So here's all the work we just did again for both of those problems. I'm going to scan this PDF in and put it on Haiku so you can reference it if you'd like. Alright, so the last thing we need to review is radicals. So what we mean by that is, we used to talk about how when things were squared, like 3 squared, that's really 3 times 3, and that gives us 9. So we would say that 3 squared is equal to 9. Now, radicals is moving in the opposite direction. So if you hadn't started at 3 squared and instead had started at 9, and I said, well, can you tell me what the square root of 9 is? You're taking the root of 9, and this sign here is a radical. So radical 9 means what is the root of 9? And we know that that would be 3. And the reason why is because we know that 3 squared makes 9, so the root of 9, what's that piece that multiplies by itself to get back to 9, is 3. Now, we can have things under the radical sign that are not perfect squares like this. So we said root 9, we got a perfect clean answer of 3. This would be our answer and we would be finished here. But we're not always going to have something that's that clear. So let's say instead we had root 24. Well, we know that that's not anything perfect because if you think back to what it could be, 3 squared is 9, 4 squared is 16, 5 squared is 25, And none of those are 24. So we don't have a perfect answer for this. So how can we solve it? Well, there's two different ways you can do this. One way is we can do a factor tree. So what we're going to do is try to figure out all of the factors that go into 24. So you might first think 2 times 12, and then you could say 12 goes into 2 times 6, 3 times 2, and now I think we've hit all of our prime numbers. So remember the rule with this, and you can think of it in two different ways. One way you can think of it as a dance floor. So you have to have a partner to go on the dance floor. If you don't have a partner, you can't leave the dance, or you can't get onto the dance floor. So I have a 2 on the end of a stem here, and I have another 2 on the end here. So a 2 can come out to the front. So these guys are going to leave, so I'm going to have a 2 on the outside. And then I have a 3 left and a 2 left, but neither of those have partners. They're all alone in their number category because these guys have already left. So I have a 3 and a 2 left, so on the inside I still have a 3 times a 2 because they weren't able to leave. So when I simplify this, I get 2 times the square root of 6, and that's as simple as I can get here because 6 does not have any perfect square roots and none of its factors are able to come out either. Alright, so to do some more practice with larger numbers and figure out how we can simplify them, let's work through these 3 examples. So root 125, again you can start to make your tree. Because it ends in a 5, I automatically know 5 is going to go into it. So you can use your calculator or do it by hand and see that 5 goes into 125 times 25 times. Now, there's 2 things you can do from here. One, if you recognize that this here is a perfect square, because we know 25 is really 5 times 5, once you find a perfect square, you know you can just take its root out to the front. So if I see this 25, I know a 5 is going to come out. If you want to break it down further, you can see that same process here. Here's a 5, here's a 5. One of them can escape, and I have a 5 on the outside and a 5 left over. The 5 here that's left over comes from this 5 that didn't have a buddy. But the key thing here is that if you can notice a perfect square early on, you can stop making such a long tree and instead take out the root to the front and be done with it. 25, you don't have to expand it down very far, but if you had something like 64, if you can realize that the root of 64 is 8 and not break down 64 into lots and lots and lots of branches, it's much easier for you. In fact, let's do an example of that really quickly. So, what if we were taking the root of 192? Now, this is even, so 2 goes into it, and I'm actually going to guess that 4 probably does go into it as well. Okay, 4 and 48. And then for 48, let's see, 16 goes into 48 3 times. So we have a 16 and a 3. So right now, what you could do is you could keep breaking down this 4, and you could keep breaking down this 16, but what I've discovered here is I have 2 perfect squares. 4 is 2 squared, and 16 is 4 squared. So if I can stop that process right here instead of making a really long tree, I know the 4 is going to turn into a 2 if it leaves, and the 16 is going to turn into a 4 if it leaves. And all I have left here is this 3. Now, if I have 4 and 2 on the outside and I have a 3 left on the inside, I'm going to get 8 root 3. And our process was cut down because it didn't take as long for me to find all of those little tiny baby factors. All right, so let's look at this one, 243. I see a 24 and I see a 3, so I'm going to guess that 3 divides into this. So check that with your calculator. Do 243 divided by 3. And you'll find that 3 goes into it 81 times. So this is where that perfect square comes into use again, because if you can automatically look at 81 and say, oh, I know that's 9 squared, you don't have to keep breaking this down. You can just say that 81, since it's 9 squared, the root of that is 9, so a 9 has escaped, and there's a 3 left over. So this would give you 9, and the 3 stays inside. So 9 root 3. And then lastly, this is kind of a strange number. It's not even, it's not a 5, it's not a 0, so it looks like we're going to be limited of things that go into it. But I do see a 14 and a 7, so it probably divides 7. So again, you can use your calculator or do it by hand, and 7 goes into 147 21 times. Neither of these are perfect squares, so I'm going to break this down again. And now I've hit all my prime factors. So 7 and 7 is a pair, so a 7's going to come out. And all that's left inside is 3. The last thing I'll leave you with is that it's really important to remember your perfect squares. So 1 squared is easy, it's 1, and then we have 2 squared, 3 squared, 4 squared, etc. So all you do is you take, I'm going to do the first 15 numbers, and you just square them. And it helps if you can remember what these are, because if you can remember them, and you can identify them as you're breaking down a factor tree, you're going to save yourself a lot of time of breaking things down to be really small when you could have seen something sooner. And a lot of these you already know because of your times tables, but being familiar with them and knowing what they look like will help. The other cool thing about 13 squared and 14 squared is they're kind of the flip of each other. So 13 squared is 169 and 14 squared is 196. And then 15 squared is 225. So I would remember these because if I have a root, for example, let's say it's 242, well, that's double 121. So if I can see that right off of the bat, and I remember that 121 is a perfect square of 11, then I know that this is going to turn into an 11 when it leaves, and my answer to this would be 11 root 2. And that'll save you a lot of time and headache instead of taking 121 and trying to find other factors to get down to 11.